It's time for Class N, the Dirac delta function. Now, when I first started teaching at UNCA many years ago, I had a double major in math and physics, and when I was teaching quantum mechanics and presented the Dirac delta function, he talked to his math instructor about this, showed him the book, showed him the notes, and was telling me that this is not proper mathematics. So I go upstairs to see Jack Wilson. Talk to Jack, and Jack's upset with the treatment. This is like mathematics. It doesn't make any sense. It's not right. And then I remember I had a book by Budkoff, Mathematical Physics, that treated the Dirac delta function in a way that was more rigorous. And when I mentioned that to the mathematician, in other words, the problem with the Dirac delta function is that you have a function that's zero everywhere except at the middle point. It's at infinity. Now, like, what is that? Like what is going on here? In other words, how can you have zero everywhere, and then when x is equal to zero, the point is at infinity? It makes no sense. So what this mathematical physics book did, and that's what we're going to do, is it takes a Gaussian and makes the Gaussian taller and thinner. And as it does that, it then approximates the idea of having all points that are zero except for the one at infinity. And that's a continuous function that has derivative at all points, and the mathematician was happy. So that's what we're going to do. Now, that's not done in the traditional physics course. They don't have time to do all that, but we're going to have time to do it here. So I hope you will enjoy that part. We'll be cleaning up here. And then we'll, in the process, we'll talk about the Gaussian and statistics, which is very, very important in all fields of study. So in statistics, this is important in all aspects of life, because statistics, when you gather data and make plots, you tend to form a Gaussian distribution when you have a population and you're taking measurements of someone's height, say, or someone's weight, something like that. You get this referred to sometimes as a bell, kind of shaped curve. So we're going to look at that, and that shows up in quantum mechanics, Gaussian. But a lot of times physicists don't realize how powerful they are when they do for example, expectation value and dispersion and things. And Heisenberg uncertainty principle and advanced quantum mechanics, they're really doing statistics where they're calculating the standard deviation, and they have the mean and variance and all that. So we'll straighten that out so that you understand the Gaussian and probability in terms of how it's applied in other fields. Okay, so there's a lot of richness in this class. The Dirac delta function is the main thing, and we're going to clean up after physicists here so we're not sloppy. We'll get a little more precise, and our Gaussian integrals from earlier in the course will be helpful in doing that. And we'll also do statistics. Let's go. Chapter N, the Dirac delta function. N1, we'll go right to it. The Dirac delta function. Here's Dirac again. We saw the Dirac equation in a previous class, and now for the Dirac delta function, the function that makes mathematicians nervous. And here's why. The function delta of x is going to be 0 if x does not equal 0, and it's going to be infinity if x equals 0. And the integral of the function over all of the x is equal to 1. Now, what is going on? No. You can't do this. How are you going to take an area if the function that you have has all these points down here, you have 0, and then here you just have a point at infinity? Like how are you going to do an area? It doesn't make any sense. But what physicists are fond of doing here is to use the box function to proceed. But we're going to even do better than that when we look at a more rigorous treatment of this whole idea. But this is so powerful in physics, just to use this method. That's why the physics classes will do this and not worry about the mathematical rigor. So what we do with the box function is we consider the box. And the box will have a delta for its width and 1 over delta for the height. So this is the height. And then as the delta gets smaller and smaller, say this is going to get taller and taller, and we're going to get this idea from the box function. But here I can do an integral because the area for the rectangle would be the height or length times the width, 1. So I got this condition here. And I have this condition as I take the limit as delta goes to 0. Well, I sort of, but we're going to make that more mathematically rigorous in this class. So this box function, the way you would define this is you would say the box function, and I'll just say delta with the delta width, is 0 outside the delta region, and this is 1 over delta inside the delta region. Then when I do my integral from minus infinity to plus infinity of this family of boxes, since I'm going to do the length times width thing, I'm going to get this equal to 1. And then I could say that the limit when the delta goes to 0 of this box family, that's going to be the Dirac delta function. Now, one important property is the sifting property. The sifting property. And to understand this, it helps us to recall the mean value theorem. Say if you have a function, say I have some kind of a function, just doing its thing like that. And this is the origin. This is y. This is x going out this way. Then if you wanted to take, say, an area in here, the idea of the mean value theorem is that there's one value of this function that you could use. Now, if I were to blow this up, say, we have something like this. And if I wanted to take the area here, I could find, let's say if I did something in the middle here. Say if I did something in the middle there and took this and stuck it over there, then I would have a rectangle. So I have a rectangle, and then this height here would be some, say, f, this is f of x. this is some f of c. So in other words, what I could do is I could take this, say this is a delta here. I could find the area by taking, not exactly an average, but kind of like an average height, and then that would take care of it. So see, here's the problem. This is not a rectangle, but if I say did something like this and put that over there, then I would have my rectangle. So that's the idea. So that's the mean value theorem, that we can do that. Okay, now given that little review there of some calculus, then if we look at, say, a box function here centered over 0, and this is delta width, and your height here is 1 over delta is going to be the height for, let's say, going from the top to the bottom. That's going to be 1 over delta. Then if I had some function like going across here, and I were to multiply the functions, then I could use that principle that there's some value here that I could find, some f of c, that would make that product work. So I'm going to go here minus infinity to plus infinity, and that box is going to be quite narrow, dx. But by the mean value theorem, there'd be some f of c that would work with multiplying, say here, I'm going to take this is going to be 1 over delta. This is going to be delta. And then this, some kind of like an average value would make it work. In fact, if you think of this height for the moment just being 1 unit high, then it's a similar idea where if you want to have, the area, because this is times 1, you would want some value here. Take this, maybe stick it down in there, for example, and that height would work. So this is f of c, but then if you take the limit as the delta goes to 0, you're going to squeeze in, f of z is going to be squeezed in to be 0. So in other words, taking the integral from minus infinity to plus infinity of the box function here, multiplying by some function with the mean value theorem, that's going to get me, it's going to squeeze this to 0, because it's going to squeeze shut. So therefore, we can write down this result if you have the Dirac delta function, because that's what this would be in the limit. It would be the Dirac delta function. F of x dx would be equal to f of 0. That's sifting property. It's sifted out where x is equal to 0 of the function. Then if you were to play the game where you move the box function down the road like this to some point A, then what you would do is your delta function, remember if you want to shift something to the right, it would be then x minus a. We've done that shift before. So then if you did the integral of delta x minus a with f of x dx, that would sift out, that would squeeze shut on a. So that would be f of a, the more general case. And if a is 0, you would then get this top case. And physicists are perfectly happy with this. Mathematicians are not. And in order to help do it more rigorously, I need to talk about the Gaussian. And this takes us to the topic of probability, and a topic that will be very, very useful for us. So here is N2, and N2 is going to be the dartboard and the Gaussian. There's a professor that works at a high school. We have a really cool high school in Durham, North Carolina, the North Carolina School of Science and Mathematics. And I found Dr. Dan Teague had worked out a derivation of the Gaussian, where the Gaussian can come from. And I love that, because usually the Gaussian is presented, but in this way, we're going to show it a nice derivation. I did this with high school students. They're teaching calculus in high school, and they use the dartboard here. You use the dartboard to like work this out. So that's what I would like to do. And before I do that, let me give you some definitions. Remember that when you have the probability distribution, some p of x and x, the area under the graph will be 1, because that'll be all the possibilities. But if you look at a little strip here, where this is x and this is x plus delta x, then p x dx gives the probability that you are between x and x plus delta x. All right, so some kind of a probability distribution like you might find in quantum mechanics, where most likely the particle is going to be around here, and less likely, to the left and to the right. And the area under the graph gives the probability between 2 points. So if you wanted, for example, to go, say, between, say, x1 here and x2, and this is going to be useful in statistics, then you take the area, and that area will be the probability that you'd be between these values. And see, most probability would be there. But if you wanted to have the range, you would take the area. And if you take the area of everything, then it's 1. So it's probably that you're going to have a value somewhere. And this can be like your people's height, for example, or weight, say, and the most probable, weight is, say, there, or the height. And then this would give you the folks. Well, here I got something negative, so this wouldn't be height, but you get the general idea. So then if you want to have the mean or the average, what you do is you take the x value and hit it with the probability that you'll be between x and delta x, and then integrate, and that gives you then the average. And then they have here the variance. This is the mean or the average. And then if you want the variance, sigma squared, and these are definitions we could put down like that, definitions here. This would be, look at how far you are away from the mean, square it, and find that probability there. So what we're saying here is, if you look at, say, this one we just had up there, and say we look at a different one, it's something like this. Then when you start taking the differences from the mean, say here's, say the mean, well, it's the most probable, but if this is symmetric, that would also be the mean. So you're going away and then finding the probability. So if you go far away and you find a lot of probability, hey, that's a big spread. If you have something like this, say, that's more narrow, then if you go away, let's say it's symmetric, so that's the mean right there. Then if you go away, far away, the probability is not as great. When this was being introduced to me, when I was an undergraduate, I asked the professor, why not use the absolute value? Isn't that what you're interested in? Because then he took the square root of this thing. I said, why not just use the absolute value? And then he thought for a second and says, well, that's messy. It's messy to do integrals with the absolute value. So this is a measure of the spread, the variance, how say the weights or the heights, things vary in the population. Okay, now it's time for the dartboard game. And we're going to throw darts and look at a region, specific region here. So, got myself here a dartboard, and I can go ahead and put in like an X and a Y. And I'm going to look at here a little square, a little patch, where this is your delta Y, and going this way, left, right, is your delta X. And the probability of being, here is X, away from the origin, you know, between X and the X plus delta X, like we did earlier, that would be this. But if I want the probability also of Y and Y plus delta Y, then I would multiply the probabilities. That's the probability that would throw a dart there. And as you get farther and farther away from the center, it's going to be less likely the dart's going to end up way far away. So that's the probability that we have there. But what I would like to do is think about a ribbon, like if I went all the way around, you know, the probability, if we're going to look at, say a ribbon, and all things, you know, being, you know, equal, that the probability is going to be the same, you know, to hit any place that's R, you know, away. And to help to get into the polar coordinates, now I'm going to use the polar coordinates here where the mathematicians like to call that theta and R. So when they have the polar coordinates, say this is Y and X, they like to do theta and R. When we were doing 3 dimensions in the plane, we call that phi, and we reserve the theta for the one that came down from the Z. We call that theta. And the one in the XY plane we call phi. But now we're going to use the standard polar coordinates. We're going to use theta. So we're not basically doing this one. We're going to use this one here. So then a dx dy would become here r d theta dr. When you think in terms of the polar coordinates like this, where this is a dr, you know, you're going down there like this, and there's your r, and this is a d theta, then r d theta is your side with dr, that's your area. So if we do that, then we can look at, say, px, py, and put in r d theta dr. And if I really don't care, see the angle, I'm going to be looking at this constant r, fixed r, so I could actually integrate over the angle and wind up with 2 pi r dr. In other words, 2 pi, you're simply not caring about the angle. I can integrate over all those. And with the fixed r, then you're going to have here the same stuff over here, same probability. In other words, when you put your r in there, in other words, this here will be some function, say, of r. And then you're thinking the probability of being between, you know, r and r plus dr. So that means we can write some g of r as being equal to our probabilities in terms of the x and y. And since this is not a function of theta, we can write down the partial of g of r, say with respect to theta, is going to be 0. It's like doesn't depend on that. R is going to be is independent of the theta. And here, if we did this on this side over here, we would get the partial of px with respect to theta times py, product rule. And then we would get the px and then the derivative of py with respect to theta. And that has to equal 0, since we're basically writing down what this is, working it out. Now, if you wanted to look at this in terms of, say, chain rule, since the p is only a function of x, it would be dp dx, and then the partial of x with respect to theta times py. And then here, the px, you would have over here dpy dy, and the partial of y with respect to theta. I really like this derivation. Then what you do is you remember that when you go to polar coordinates, you know, when you have your r and you have your theta, this is a nice review of basic math. Then this is your x, that's r cosine of theta, and this is your y, which is r times the sine of theta. So if you want the partial of x with respect to theta, that would be minus r times the sine of theta. So that's what this would be here, minus r times the sine of theta. Then if you want the partial of y with respect to theta, that's r cosine of theta. So if you did this one, you would have r cosine theta. That's what this one is over here. But notice this, r sine of theta is y, so actually this is minus y. And r cosine of theta is x. So this is actually x. Now, before I write this again, I would like to use notation that this is p prime of x, the derivative, and then over here, this is p prime of y, the derivative. So then I would have a minus sign and p prime of x, and then I would have a y, and then this thing would come down as the p of y. Then over here, I would have the p of x, then I would have the p prime of y, and then I would have the x equal to 0. So now I can write down on either side of the equation, watch this, we'll just go ahead and write down p prime of x, y, py equals px, p prime y times x. In other words, just put this on one side of the equation. So this is one side of the equation, and then this is the other side, and add it to the other side. And then here, get all the x's by itself on one side of the equation. And we can do that by dividing by x, px. So if I divide by x and px, I would and also y and py. In other words, we're going to move this to the right side, and we're going to move the x information to the left. So this would be then p prime of y over y py. So we took this and put it under the p prime y. Then we took the x stuff and put it under the p prime x. So you got this cool relationship. But since x and y are independent of each other, it's equal to some constant. It's equal to a constant. So that means if we look at this, let's go over here and say then p prime of x over xpx is equal to some constant. And now let's solve for the p. Well, this is 1 over x p of x, and then I have the derivative of p of x dx is equal to some constant. And then I could write this as 1 over p of x dp of x, bringing over to the right-hand side the x and this dx, like you're separating the variables out. So dp over p, and then x dx going over to the other side. Then we can do some integral here. We can integrate. That's the left-hand side, and the right-hand side would be the cx dx. So this would get you a log of px, and then this would get you a c constant. This is x squared over 2 plus another constant of integration, which I'll call little c. Okay, that means that the p of x, the probability, this is amazing. We're getting the probability function of x, like we're getting it, like it's coming out of here. And it's going to be a Gaussian, watch this. So this is going to be equal to all this with the exponential. So this would be big C, x squared over 2 plus the little c. So if you take the natural log of this left-hand side, you just pull down what's up there. Now watch as we go on. We can write this as a product of 2 exponentials with the little c, since when you multiply e to stuff, you add the stuff. And then we're going to call this constant a. So then the probability distribution is a, e, I'm getting myself the Gaussian. Now, I just think this derivation is so cool. Now, by common sense, we know the probability as we shoot the darts. If we're going to be a kilometer away, like it's not going to work. It's going to be less probable. So in other words, this c is a negative. So I'm going to put down negative k where k is greater than 0. So that's by the mathematics, the probability. So therefore, the p of x is now a e to the minus k over 2 x squared, all right? And that's the Gaussian. That's the Gaussian, and that's the bell-shaped curve, like we got it. And then we're going to normalize. If we go from negative infinity to plus infinity, the probability's got to be 1. So that means here, if we integrate from minus infinity to plus infinity, e to the minus k over 2 x squared dx, this has to be 1. But see, we know what this is because remember we did this integral I earlier in the course, minus infinity to plus infinity, e to the minus ax squared. I'm going to use alpha here. I feel like using alpha. And that was equal to the square root of pi over alpha. So that means this integral in here, this one in here, this has to be the square root of pi over this alpha, which is k over 2. So that 2 would flip up, that's 2 pi over k. And that's basically saying that your a over here times the integral result, which is the 2 pi over k, that has to equal 1. Well, if that has to equal 1, then the a would be, it's flipped. It would be k over 2 pi. That's our normalization constant. So therefore, p of x, the probability distribution, is our constant over 2 pi e to the minus k over 2 x squared. Amazing. Look at that. And if we want to find the mean or the average, if we go from minus infinity to plus infinity of x px dx, since this is an even function in x and this is an odd function, we're going to get 0. And that makes sense because this is an even function. You know, the Gaussian does something like this. It comes up like this and goes down like that. So that's the probability distribution. And by just looking at it, you can see, because of the symmetric, that the average is going to have to be right smack in the middle. It's going to have to be, in other words, mu is going to equal 0, like that's the average. So we have the average is 0. And now what about the variance, which by definition is x minus mu squared p of x dx? Well, this is actually going to simplify because due to our symmetry, the mu is 0. So this is going to simply be here. We're going to integrate, and we'll be going from minus infinity to plus infinity, x squared times the probability function. So this is going to be integrate from minus infinity to plus infinity, x squared times the square root of k over 2 pi, and then e to the minus k over 2x squared dx. But we know how to do this kind of integral. In fact, we did it before. This integral that we're interested in, say, minus infinity to plus infinity, the main idea is this x squared with e to the minus alpha x squared. What we do is we take a negative derivative with respect to alpha. We take alpha as now a variable, minus alpha x squared dx. And we know what this is. This is the square root of pi over alpha. And then if we take the derivative, so we have simply this, square root of pi over alpha is this. Take the derivative with respect to alpha, you pull down a 1/2 with the minus sign, cancel that minus sign. And then you'll have the square root of pi floating around. And then you'll have alpha to the minus 3/2. And what we did way back, we wrote that as 1 over 2 alpha, square root of pi over alpha. So this has alpha to the 3/2 down in the denominator because of the minus sign, square root of pi and 1/2. So using this result, which we just derived, this one here, and this is the integral that we want, we can see that we can pull out the square root of k over 2 pi and then have the integral of which we know the answer. So here, we know the answer to this. It's going to be 1 over 2, but then like what's the alpha? The alpha here is k over 2. So I need to have 1 over alpha, so that's going to flip the k over 2. Then I need to have a square root of pi, and then I have to have an alpha down in the denominator, which would be, it's going to be your k over 2. So that means for the variance, we're going to have the square root of k over 2 pi coming from here. And these are going to cancel, these 1/2. So this will be 1 over k. And then that 2 is going to come up in the top, 2 pi over k. And then if you look at these two things, they're going to go away, cancel. Oh, you have this really beautiful result. That's a very nice result. So let's go back and write down our probability function, which is a square root of k over 2 pi e to the minus k over 2 x squared. And now what we're going to do is we're going to replace the k, because the k is 1 over, this is what they do in statistics. They use this variance. So that means the probability function. So I'm going to have a 1, the k is going to be 1 over, so I'll have a 2 pi, and this is going to be this sigma squared, the variance, and then e to the minus x squared over 2 sigma squared. So whenever there's a k, I put 1 over sigma squared. So there's 1 over sigma squared and a 1 over sigma squared. And this is the formula which we can now look at if we do our shifting trick. Remember, that's the Gaussian that's centered over 0. So if we want to send it down the road, say a mu, say the average is not going to be the center, it's not going to be 0, it's going to be down the road, then all we need to do is do the shift, and we know how to do that. 2 pi sigma squared e to the minus, we go x minus mu. That's the shift. And I prefer to write this like this, where I put the square root down here, personal preference, and then have this nice result like that. And that is the Gaussian probability distribution, which I have it neatly in the book here, written and boxed off. So let's do some application here. Let's do some application here. The Gaussian in statistics. And I have the book here. Look at this is a nice graph of the Gaussian, shift it to the right, and this here is a little bit easier to see what's going on. In this particular case, what they did is they put the center at 0, and then these are your remember we did the variance, we take the square root, and that's called the standard deviation. And this is very nice because it's a general principle that if you're between -1 and +1 standard deviation, you're getting 68%. So there's this rule that they learn like in social science, the 68, the 95, and the 99.7 rule. So if you're between minus standard deviation to a plus, you got 68% of the population. Say you're measuring height, how tall people are or something. You have some curve here with the areas. And then if you want to go 2 standard deviations on either side, that's the 95%, or more precisely 95.44. And then if you go 3 standard deviations, you're at 99.7. So that's kind of neat. And that's very important in social science. And now it's time to clean up the Dirac delta function. And this is going to bring us to a delta sequence of Gaussians, and that'll make the mathematicians happy. Since the Gaussian's a nice smooth function, continuous, and you can take the derivative everywhere. So we're going to take here our Gaussian and write it down again, 2 pi variance, and then e to the minus x squared, e to the minus x squared over 2 sigma squared. And what I'm going to do here is go to Wikipedia, where I found a cool sequence, and what they did there, and I'll go ahead and use their notation, a squared is 2 sigma squared. And if you do that, then they came up with a sequence of Gaussians with that a parameter, where this becomes 1 over, take the square root of the 2 sigma squared, you pull out an a, and you have the square root of pi. I have graphs that go with this, so we're going to use this convention from the Wikipedia. Then this is e to the minus x squared, and then the 2 sigma squared. That looks cool, just like an a squared. It's nice. That's nice. So if we do that, and then go to Wikipedia and see what the graphs look like, we see that as the a gets smaller and smaller, then you get a more peaked Gaussian. And you can understand that because if you divide by a small number, this is going to get bigger. And in here, if you divide by a small number, like if you have, say, here over some kind of super small number, then you're going to get minus some, you'll have x squared, but then you'll have a super large number times x squared. And that super e to the minus, if you have e to the minus large, you're getting really small. You're suppressing. That's why you're suppressing. You're going to get small like 0. So e to the minus some big number is going to be like 0. So that's why when the a gets smaller, you get down to 0 fast. And this is looking more and more. See, in the limit, this is going to be the Dirac delta function as we get smaller and smaller and smaller. And the mathematicians are happy. It's nice. So that's the secret, to show that you can write the Dirac delta function as a limit of a sequence of Gaussians, and the Gaussians are continuous and differentiable. Very nice. So the last trick for the day is going to be to show that the Dirac delta function can be written as an integral. All right. So now we're going to go back and use something from earlier in our course. That's what I like about those integrals that we did earlier. If we look at, for example, this integral plus I kx, and this is just another k thrown in there. We did this integral before, and we got this result. Okay, we're going to use a. I think, we used a before. We're going to use alpha. We'll use alpha now. Okay, so here, what I want to do is I want to use that integral, and I want to swap variables just to have different notation. I want to replace, x and k. I want to flip x and k, and there's no problem doing that. So this is minus alpha k squared plus I, and I flip these two, I still get the same thing there. But now x becomes k, and this is a square root of pi over alpha, and this is minus x squared over 4 alpha. So there's nothing wrong with doing that. We're just redefining what we mean by x and y. And the reason why I did that is because I want to work with this form with the x squared, since this is what I got like up in here. I got this kind of stuff up in here. Okay, so what we would like to do is write down the delta going back here. I want to put back the 2 pi sigma squared e to the minus x squared over 2 sigma squared. So I'm going to label these with the sigma, because when I play with the sigma getting smaller, and when the spread gets smaller, I get myself a narrow and taller situation. All right. What we're going to do to use this, we want to identify 4 alpha with 2 sigma squared. So if I do that, then I'm going to write this one again here. This is from minus infinity to plus infinity, e to the minus. Well, what happens to alpha? Well, let's look at that. Alpha would be 2 sigma squared over 4. This is sigma squared over 2. So that's what has to go in here for the alpha. Sigma squared over 2, and that's hitting a k squared, plus ikx. Later we'll learn that's Fourier transform language. And that's going to be on this side. If I look at this alpha, 1 over alpha is going to be 2 over sigma squared. So I need here the square root of pi over alpha, which would be the square root of pi. Actually, this is 1 over alpha, so I would just put a 2 there and a sigma squared like that. So that's what this is going to be. I just replace it with that. So it's the square root of 2 pi over the square root of sigma squared. And then what I have here is the 4 alpha, which is this. So minus x squared over 2 sigma squared. Now, to get the delta sequence, what I would like to do on this right-hand side, to get this delta sequence on the right-hand side, I need to multiply by 1 over 2 pi. So if I multiply by 1 over 2 pi, then this right-hand side is the delta sequence form, because 1 over, it'll bring the 2 pi downstairs. So let's do that. So 1 over 2 pi times this integral, e to the minus sigma squared over 2, and the k squared is there, plus the ikx dk, and this will be 1 over 2 pi, and then this will be the square root of 2 pi over the square root of the sigma squared, e to the minus x squared over 2 sigma squared. Almost there. And then what we would have here for the right-hand side, 1 over the square root of 2 pi sigma squared, e to the minus x squared over 2 sigma squared. And that's it. Exactly the same. So by being patient, we're going to have a good, nice result here. So that is a delta sequence. So therefore, I have found that the delta sequence, by being very careful with these variables, how I was changing them, can be written as an integral. 1 over 2 pi minus infinity to plus infinity, e, this thing, like that. Notice that this integral is over k, and it's a function of x. Now, I thought I would end this class by letting the mathematicians get worried. Now watch this, because this is so far good. They're going to be fine with this. But if I go the limit here as the sigma goes to 0 to get the Dirac delta function, so the limit of the sequence, and the mathematicians will still be fine with this. This is okay. This is 1 over 2 pi, the limit as sigma goes to 0. Okay, but the punchline's coming up. E to the minus sigma squared over 2 k squared plus ikx dk. Now we're going to get folks upset, because if I actually come in here and actually do it, if I actually do it, this becomes e to the 0. That's 1. So if that's 1, then whoa, watch this. I get the delta function is 1 over 2 pi, innocent looking equation, minus infinity to plus infinity, e to the ikx dk. Because e, this term here, you know, e to the minus 0 when the sigma goes to 0 is going to be 1, and I'm going to be left with just this. And that is very disturbing, because this is sines and cosines. How could you integrate like sines and cosines and like get something crazy like the Dirac delta function? But see, when a physicist writes this down, and they do it all the time, we clean up after the physicist by saying this really means what's above here. And what's above there is okay, you see, and then the sequence of the Gaussians, okay. But you'll encounter this in physics classes. But let's look at this and play around with this thing for a second. Suppose I were to integrate this thing, I would go e to the ikx over ix, since I'm integrating here with respect to k. All right, so here, if I integrate this thing, let's go ahead and check it. If you take the derivative, the ix comes down because you're taking derivative with respect to k. That cancels, so you get that. But see, if you So looking at this more carefully, this is a nice, well-defined sequence. But this, when you take that sigma to be 0, and you have e to the 0 as a 1, now what is that? This will make mathematicians nervous. I mean, what is this thing? How could that possibly be the Dirac delta function? I mean, this would be e to the ikx. You're integrating with respect to k, so this is an I over x. And if you go from minus infinity to plus infinity, let's check this first. If you take the derivative with respect to k, you pull an ix down, it cancels. So that works. But see, you're putting in here the x is not relevant here. It's really this k. You're putting in for the k. But see, this is going to be cosine of kx plus I sine of kx. So, like, they're just going to go from 1 to minus 1, 1 to minus 1 each. And how are you even going to get, like, 0? Like what's going on? You're at infinite? Like, it doesn't make any sense. So mathematicians will get quite concerned about this situation. And then if x should equal 0, if x equals 0, then you're integrating from minus infinity to plus infinity dk 1 over 2 pi k. You know, that's like what is going on here? Now physicists might say, well, that gets you my infinity, but how's this getting you 0? I mean, how's that get you 0? Like, it's not good mathematics here. So this should be interpreted that it's really a limit of this sequence where things are behaved here. This Gaussian here shows up. Gaussian shows up there, it's good. So, nice formula. Physicists use it all the time. So, integral form for the Dirac delta function. That's it for today.